Okay, this is the practice problems number 7. It tells us that a 35 kilogram block is sitting on a table and is connected to a bucket by a massless rope that runs over a massless frictionless pulley as shown in the diagram. So you already have the diagram in front of you. I'm not going to redraw it. The empty bucket has a mass of 2 kilograms. The coefficient of static friction between the block and the table is 0.38 and the coefficient of kinetic friction is 0.29. Part A is telling us that sand is gradually added to the bucket until it begins to move. Calculate the mass of the sand that needs to be added to the bucket to make it move. Part B asks, once the bucket begins to move, no more sand is added. Find the acceleration of the system now that the block is already moving. I'm going to start by listing what we're given. We know that the block is 35 kilograms. I'm just going to call that mass 1. We know that the empty bucket, I'll call that mass 2, is 2 kilograms. You know that the coefficient of static friction is 0.38 and the coefficient of kinetic friction is 0.29. And we are looking for, in part A, added mass. So this is mass of the sand. And in part B, we're looking for acceleration. So this is a modified Atwoods machine. I'm going to start with the force diagram for each of these two things. So starting with the force diagram for the block. And we want to look at it before it's moving because in part A, we're looking up until it starts to move. So if it's at rest, your forces need to be balanced. Going to the right, we have a tension force. Going up is a normal force. Going down is a gravitational force, and going to the left is going to be a frictional force. And because the bucket and the block are not moving in part A, all of your forces should be balanced. For the bucket, only 2 forces acting on it. You're going to have an equal tension force as the one on the block, so Ft going up and Fg going down. Because it's at rest, all of your forces are equal. So Fg equals mg. You know what the weight of the bucket is. It's going to be equal to the tension force, which will be equal to this tension force, which will be equal to the frictional force. So what we need to figure out in the end is what this weight is, all things considered, with the added sand. So we're going to start by looking at what the mass needs to be to keep everything at rest, so getting it to just start moving. We know that frictional force is equal to mu Fn. We know that for the block, our normal force equals Fg, and Fg is just 35 times 9.8. So this Fg is equal to 343 newtons, which means that the normal force is also equal to 343 newtons. So frictional force is equal to mu. In this case, it's not moving. We want to use the coefficient of static friction. So 0.38 times the normal force, 343 newtons. This is equal to the frictional force, 130.34 newtons. So frictional force is 130.34 newtons. Again, because it's not accelerating, this is also 130.34 newtons, which means that because the tensions are equal in the pulley system, this is 130.34 newtons, and my weight is 130.34 newtons. Fg equals mg, so weight divided by g will give me my mass, 130.34 newtons divided by 9.8 newtons per kilogram equals the mass. So the total mass of the bucket plus the sand is 13.3 kilograms. It's asking for how much sand needs to be added to the bucket. So the mass of the sand would be the mass of the total minus the mass of the bucket So 13.3 kilograms minus 11 kilograms. So this is equal to, sorry, this should not be 11. This is minus 2 kilograms. So this equals 11.3 kilograms. We only have one sig fig, so the mass of the sand is approximately 10 kilograms. So because, again, this was at rest, we knew that all of our forces were equal. You were given enough information to solve for frictional force. You had the normal force, you had mu. Once you found the frictional force, because of no acceleration, frictional force equaled tension force. This tension had to equal this tension force because a pulley only changes the direction of the force. Tension equaled weight. What we solved for was the weight of the bucket plus the sand. So finding the mass of everything, 13.3 kilograms, subtracting the mass of the bucket, we got the total mass of the added sand. Now let's look at part B. I need to draw separate force diagrams for part B. Because now it's accelerating, not everything's going to be balanced. So for the block on the table, we have tension going to the right, a shorter frictional force to the left, normal force going up, and gravitational force going down. No acceleration in the y direction, so those two are equal. It is accelerating in the x direction, so this will be where my unbalance is. If we look at the bucket, and this is the bucket now with the sand, the tension force is equal to the tension force of the block, and we have a longer gravitational force going down. So the net force equation for the block, I'm going to call this F net 1 equals right minus left, Ft minus Ff. For the bucket, this is the net force of 2 equals top minus bottom, Ft minus Fg, and that's Fg of 2. Our tensions are equal, so isolating the tension force, we get F net 1 plus Ff equals Ft, and over here, F net 2 plus Fg2 equals Ft. Setting those tension forces equal to each other, we F net 1 plus Ff equals F net 2 plus Fg2. F net is equal to mass, so this is mass 1 times acceleration plus my frictional force, equaling F net 2, this is mass of 2. In this case, it's accelerating down, so I need to make that acceleration negative, plus m2g. Mass 1 times acceleration, getting all the accelerations to the same side, plus mass 2 times acceleration equals m2g minus the frictional force. Factoring out the a, we get a m1 plus m2 equals m2g minus ff. So acceleration is going to equal m2g minus frictional force over m1 plus m2. We know that frictional force equals mu Fn, and in this case Fn is equal to mg, so this is equal to mu m1g. So my frictional force equals, it's now moving, so we want to use the coefficient of kinetic friction, 0.29 times mg, which we already solved for in part A, 343 newtons. 0.9 times 343 equals 99.47 newtons. So acceleration equals the weight of the bucket, this is 130.34 newtons, minus the frictional force, 99.47 newtons, divided by 35 kilograms plus 13.3 kilograms. This will come out to 0.639, keeps on going, meters per second squared, 1 sig fig, so acceleration is approximately 0.6 meters per second squared. So part B was the modified Atwoods machine with friction. Once we developed the equation, again, not something I would memorize. Do not really count on memorizing this because there are so many different cases for Atwoods machines. But we were able to figure out what the acceleration was by looking at the net force for each of them and setting tensions equal. Not forgetting that acceleration for the hanging mass was negative since it was speeding up in the negative direction. Eventually isolating, solving for acceleration, putting the numbers in that I already had, and coming out to the acceleration for the system.